and thank you everyone for joining us on this probably best day of the year so far, weather-wise. Tonight I'm going to talk about some misconceptions about stars and how they work. Some of them have been around for quite some time. Some are more recent. And they don't come down to just simplifying topics to make them understandable by the non-expert. So it doesn't come down to just presenting the material at a level that the non-expert, can consume, and sort of leaving off some of the details. It really comes down to just the fundamental understanding of how stars work. It's just been utterly lost amongst, and if you've seen some of these misconceptions, you're in great company. Most of my colleagues don't know what they're talking about. Textbook writers, not all textbooks, but many of them are full of these misconceptions. The higher up you go, the fewer of them they have. There's one or two that have very few. There's one I know of that doesn't have any of these I'm going to talk about tonight. The introductory textbook that I use at Western for general education level, non-science majors, has fewer misconceptions amongst these here than the average one. Well, anyway, that just to sort of set the tone, you can see the little cartoon I put over here. The starfish. This is the star fruit, both named for their star shape. Well, that's a star, which doesn't look like a starfish or a star fruit. Okay. Well, Richard, I don't have advancement. There we go. Okay. So we're going to ask three questions here. And several years ago, when I began a quest to understand some of these misconceptions, I was just using Google and looking to see whose notes out there are saying what. And I just type in a question and Google come back with a whole bunch of websites. You can go to somebody's notes. It could be at Caltech, grad course, Caltech undergraduate course, Berkeley, whatever, or someone's general education course someplace. And I just began collecting them to see how widespread some of these things were. But now we have AI. It does all the work for me. The results come back as a composite. These are composite answers based upon tens of thousands of educational websites, NASA, observatory websites, various astronomy notes, people's course notes. So why are stars luminous? And you can do this on your own. You can do it right now if you wish. Pull your phone. I can almost guarantee you that in the first sentence, the word nuclear fusion will appear. Releasing immense amounts of energy that heat the star and cause it to shine brightly, neither of which are true. Energy produced by this fusion reaction is what makes stars luminous. Also not true. Nuclear fusion, primary mechanism behind stars' luminosity, heat generation. Why are stars? We'll get to the next question here about why stars are hot. This fusion process generates tremendous heat, causing the star to glow. Also not true. I mean, it's just one thing after another. Let's go on to the next question. Well, first of all, we ask AI, and then AI says nuclear fusion. Why are stars hot? And you can read the result there. Nuclear fusion. Energy produced by heat fusion heats the star's gas, causing it to glow and radiate. This is the primary process that generates heat in stars, where light elements. Okay, that's the second part's true. That's all okay. Although the last part here, releasing energy. Sorry, that's all right. But the first part there is wrong. As I said, if you've run across any of these misconceptions yourself, you're in great company. It's everywhere. Nuclear fusion. How do stars support themselves against the force of gravity, against gravitational collapse? When I say gravitational collapse, I mean that there has been a year ago, a massive, massive transport ship, cargo ship, ran into one of the two central piers of the Francis Scott Key Bridge. You've probably all seen videos. When that ship ran into that pier, there was a tremendous transfer of momentum that put tremendous strain on the structural materials of that bridge, and to the point where that bridge could not respond, that the structural materials could not respond to go back into an equilibrium. It pushed it beyond the breaking point. And once that process got going, it just avalanched to failure. Force balance failed. And under the force of gravity, the bridge collapsed, hit the water 56 meters below in 3 seconds, falling in free fall, unopposed by any forces other than gravity. That is gravitational collapse. It works the same way in a star. As we'll see, that stars are supported by the pressure exerted by gases. It's only when that pressure exerted by gases somehow fails that gravitational collapse is in play. Well, but the rest of the world, well, not the entire world, but much of the rest of the world thinks that it's fusion. Heat and radiation produced by the fusion balances out the gravitational force trying to collapse the star. Outward pressure. The energy generated creates outward pressure, pushing the gravitational force, pulling the star inwards. Gravitational collapse. With less pressure, outward pressure to counteract gravity, stars' cores begin to collapse inward. Oftentimes, radiation pressure is somehow brought into this argument because there are some nuclear reactions that happen to produce photons. These are gamma rays. And so this is somehow fusion produces radiation pressure that supports the star against the force of gravity. So again, much of what's out there on the internet and what's in textbooks, not all of them, but many of them, it's nuclear fusion. But none of these statements can explain, for example, what happens to a star in the absence of nuclear fusion. If Dr. Evil, fired his magic ray gun into the sun and turned off fusion right now, we'll look into what happens, okay? But it has nothing to do with this. And in fact, the absence of nuclear fusion is how a star begins its life. As protostars, they're neither hot enough or dense enough in their central regions for nuclear fusion to produce virtually any energy from nuclear fusion. Stars begin as hot, luminous protostars, but not hot enough. Luminous protostars in pressure gravity balance, force balance, and radiation pressure throughout the vast majority of most stars' lives, radiation pressure is negligible. I mean, it's there, and some stars it's completely negligible. Other stars, it's there, it's a little small correction. Only in the most massive stars is radiation pressure important to the pressure supporting the star. And these are very few. Thermonuclear fusion requires a star to be sufficiently hot within the central regions. We'll talk about that momentarily. And yet we're also told that it is the energy from nuclear fusion that makes the star hot and keeps the star hot. We've just seen that. Think about that for a minute before I go to the next point. Stars have to be hot for nuclear fusion to take place, to produce energy to make the star hot, supposedly. And yet the star has to be hot enough to produce energy from fusion. So fusion occurs because stars are hot, but stars are hot because fusion occurs. And this is a circular argument. It goes nowhere. It puts the It puts a cart in front of a horse and you go nowhere. These statements, and the ones we've just seen, suggest that the failure of nuclear fusion will result in the star rapidly cooling off, turning off, switching off, and collapsing under the force of gravity. And none of this is remotely useful. So before we go on, I want to just mention a few bit of background about thermonuclear fusion in stars. All right, so what is nuclear fusion? It's a fusion of two or more atomic nuclei consisting of one or more protons and neutrons. Hydrogen is very simple, it just has one proton. Helium has two protons and two neutrons, and so on. Okay, so you fuse two or more of these atomic nuclei under the strong nuclear interaction, which is a force that can occur under conditions of very high temperature, typically above 1,000,000 degrees at least. Also high density. So what nuclear fusion only takes place in the central regions of the star. We oftentimes refer to that central region as the core of the star, not the outer parts of the star. The difference in binding energy between the reactants, so which atomic nuclei you put in, those are the reactants, and which ones come out, those are the products. And the binding energies, nuclear binding energies of the reactants are smaller than the binding energy of the thing you just made. The difference in binding energy comes out as energy transferred into the surroundings in various forms. This is no different than a chemical reaction, exothermic chemical reaction. Just that for chemical reactions, we're talking about the electromagnetic force instead of the strong nuclear force, and the energy scales are different by a factor of 1,000,000 for nuclear physics compared to chemical physics. The fusion of 4 hydrogen nuclei, protons, and a helium nucleus generates 80% of the total possible extractable nuclear binding energy. So, and this is the very first step the star undergoes fusion with. It's conversion of hydrogen, the various lightest elements, into helium, the next lightest element. And in that first step, as what we refer to as the main sequence of stars, you get 80% of the total extractable energy from fusion. Okay? All that happens subsequently are very, very small amounts by comparison, which is why the star spends almost all of its lifetime on the main sequence, fusing hydrogen and helium. Nuclear fusion reduces the number of particles within the star's core because you're putting 2 or more to make 1. In fact, for hydrogen fusion, it's 4 hydrogen nuclei makes 1 helium nucleus. 4, 1, 4, 1. And on top of that, you're also including there's 4 electrons that get turned into only 1 on the other end, or 2 on the other end. So it's 8 particles becoming 3 for hydrogen fusion. So you have fewer and fewer particles that are present in the core as time goes on. And of course, you're changing the composition from initially a hydrogen-helium mix starts to begin with a very small amount of heavy elements, to initially in the center of the core of the star, at the end of the star's main sequence, we're almost all helium, and then eventually to carbon and oxygen, and then eventually to neon, if the star is able to convert carbon into neon magnesium, and so on and so forth, make heavier and heavier elements with fewer and fewer particles left behind. And as we'll see, the energy injected in the star by nuclear fusion lengthens its luminous lifetime. This is one of the attributes of nuclear fusion that is useful to communicate. But as the star changes in and becomes ever more inhomogeneous in composition, because the whole outer envelope of the star is not participating in fusion, so it's mostly hydrogen, helium, right? But the core is changing composition from hydrogen to helium to carbon, oxygen, and so on. All right? The structure has to evolve in time to maintain force balance, which we'll just define more specifically in a minute, pressure and gravity force balance. And this, in fact, is the deal. The star says, well, hey, fusion, you can lengthen my luminous lifetime? That's great. I'll take you up on that deal. And the devil says, okay, but there's something to pay. And that is you have to change your structure. And then there are consequences to that the star has to pay for. And of course, the devil is gravity here for the star. We're going to look a little bit in history, because we've understood how stars work for 100 years. We're only losing track of how things work here since the age of the internet, as far as I can tell, mostly. By 1917, we had reasonably good measures of stars' external characteristics, its distances, their masses, their surface temperatures from their spectra, their luminosities, and from these two, their sizes. We knew their surfaces were composed of gas, but the elemental compositions of stars were still being under debate in this time period. Little was known as to what went on inside. The state of their interiors was a mystery. Was it gaseous or liquid or solid? These were all the things debated initially. And then Sir James Jeames and others convinced Eddington that the interiors of stars were most likely consisted in bulk of ionized gases. So these are gases with the atoms missing one or all of their electrons because of the very high temperatures. How is the energy transported through the star? By radiation, convection, conduction. All right, that was not known. What was known is the stars are in force balance. This was known. If the star is not in force balance, it's not an object, it's an event. If it's not in force balance, it will get there really quick or lead to a catastrophe. All right, so force balance, the net outward pressure exerted by matter balances against the inward pull of gravity. This was known to be in place. Any force imbalances result in rapid changes in structure on timescales of seconds, minutes, hours, days at most. For the outer parts of extended stars, they may pulsate on timescales of days to find a new balance point. Energy balance. This is the other balancing act in stars. In the late 19th century, Kelvin and Helmholtz argued correctly that in the absence of some internal energy source generating energy in the center of the star or somewhere in the star to replace the energy lost at the surface of the star, that the star would undergo very slow quasi-static contraction. All right? I use the word contraction purposefully. We have two words in the English language that imply the motion, inward motion of material. One's can collapse, one's contract. You know what collapse means? We just talked about the bridge, Chesapeake Bay. It's a catastrophe. Everything happens really quick. It's out of force balance. Gravity is the only force acting on the material. All right? Contraction, something that happens on a very gradual, long time scale. That's exactly right. Stars that have a net energy leak, if they have no source of energy being generated in their interior and they radiate energy away in the form of light, have a net energy leak. And because of that, they will undergo slow gravitational contraction, maintaining force balance all along the way. This is the difference between, for example, your car with the four tires suspending the chassis of your car above the ground. Due to what? Due to the difference in pressure between the inside of the tire and the outside of the tire, multiplied by the surface, by the area of the tire footprint on the ground. That's equal to the weight, gravitational weight bearing down on that axle. And you can actually make this measurement, I tell my students, out in the parking lot with two pieces of paper and a pencil and a ruler. And do it 4 times and measure the weight of your car. All right, your car is in force balance, hovering above the ground. All right, but if someone actually blew out the sidewalls of your tires all simultaneously, kaboom, they all failed. The car goes go like that under the force of gravity in free fall. That's a collapse. That's in direct contrast to if you have, say, some cheap valves in your tires, and they're slowly leaking air. And so the pressure difference is slowly getting smaller. And your flat tires are slowly getting flatter. But every moment, every second in time, your car is in force balance. All right, the chassis of the car is in force balance with the force of gravity. And it just finds a new equilibrium point with a flatter tire, which can happen over weeks before you're on your rims, right? Weeks instead of fractions of a second. Orders of magnitude difference in consequence. But the contraction hypothesis, we thought for a while that stars, we didn't know about any energy source inside of stars. So we thought, well, they all just must be contracting very gradually. But this was a problem because we were beginning to discover that the Earth has been around for a couple of billion years from geology, biology, and a star of our sun's mass, present radius, and luminosity would have only been contracting for the previous 25 million years. And Eddington, in 1920, correctly deduced. This is a huge leap he made because there was no understanding at all of nuclear fusion, but we had just discovered that the mass of 4 protons, okay, was 0.7% smaller than the mass of a helium nucleus. He said, and of course, Einstein's E equals mc squared had been around since 1905. He said, aha, that must be it. I don't know how it works, but that must be it. There must be nuclear reaction taking place that converts hydrogen into helium, releasing energy through E equals mc squared. The difference in mass multiplied by c squared is the energy coming out from fusion at a rate equal to the star's luminosity, and the star is able to achieve energy balance and therefore not contract. It just will sit there for a very long time. Although then, there's still the devil to pay, as we'll say, because the star has to change structure anyway. Okay, so he went on in his investigations of stars. He presumed that the simplest equation of state governing the behavior of particles that provide the pressure was an ideal gas. An ideal gas has a pressure that is proportional to the number density of gas particles multiplied by the mean kinetic energy of a particle. It's a very, very simple, it's the simplest possible equation of state, actually, in all of, that you might describe any system of particles. And then in other terms, all right, the number density of gas particles is equal to the mass density divided by the mean mass per particle, which is, you'll see this value mu here, the mean mass per particle in atomic mass units, multiplied by temperature. The temperature, the mean kinetic energy per particle is proportional to temperature. Eddington presumed the simplest mode of heat transport, radiation transport, radiative diffusion. So rate of energy that slowly diffuses downhill in temperature. So the star would be hottest on the inside and coolest on the outside, and energy would simply naturally roll downhill, carried by photons. And that pressure, that change in radiation pressure scales as, or the radiation pressure scales as temperature to the 4th power. So if the temperature is highest in the center, the pressure is highest there. And on the outside, the temperature is lowest, so the radiation pressure is lowest. And that's the temperature gradient that the rate of energy rolls downhill. Higher temperature gases emit more photons with greater energy, and so they exert greater radiation pressure. And ultimately, it's the outwardly diminishing particle pressure, both gas and radiation, that act against the inward force of gravity to establish and maintain force balance. None of this has anything to do with nuclear fusion or the energy coming out from it. So we have a total pressure, gas and radiation in this model, where you define this parameter beta as the ratio between gas and the total pressure. And so that means 1 minus beta is the other fraction, which is radiation, the total pressure. And then the constraints of pressure-gravity balance led him to a conclusion of how to scale a temperature with a density for a star of a given mass. This is a star's mass in use of our sun's mass, raised to the 2/3 power. There's a number out here, about 5 million kelvins. And it scales its density to the 1/3 power, with density in these units here, where 1 gram cubic centimeter is the density of water, liquid water. So for some value in gas density, more massive stars are hotter. Pick a value there. 1, 10, whatever you want to pick, right? Make a more massive star, it's got a higher temperature at that density. You knew this 100 years ago. Stars are not hot because of fusion. They're hot because they're supported against gravity by a pressure whose mean kinetic energy of a particle depends on temperature. That's why they're hot. course, didn't have any fancy computers, so he can make simplifying assumptions. And although in the end, the assumptions he made were actually quite good anyway, he assumed that the ratio between radiation to gas pressure, which we'll call the script R here, and so beta, and also composition through the star, and thus the mean mass per particle, don't change with radius through a star of a given mass. And when you do that, make that assumption, you can come up with a relationship between the mass of the star and this ratio between radiation to gas pressure for a given composition, which mu is measuring something about the composition of the star. Hydrogen has the smallest value of mu. If you throw in some helium, the value of mu will go up. That's measuring mean mass per particle. Okay, so, and this is what he found. A plot of radiation pressure to gas pressure versus mass in solar mass use, 10 to 1, 100, 10, 100,000. And this is the scaling with mass. It scales as mass squared. The ratio does at low masses. It scales as roughly the square root of mass at very high masses, although we don't know any of these stars this massive. And look and see what are these numbers here? 10 to the minus 6, 10 to the minus 5. What, radiation pressure is important in stars? What you tell it? 10 to the minus 4, 3, 2, 10 to, there's 1. And that corresponds to stars that are wholly macro, really massive stars. There aren't very many of those. For a star of our sun's mass, that ratio R is about 1 part in 1,700. There's no fancy physics here, all right, that a middle school science or teacher could not, or high school teacher could not show using the ideal gas law to predict the gas pressure and a simple constant multiplied by temperature of the force to predict the radiation pressure. Compare those two numbers at the center of the sun. I don't know why we say that radiation pressure is important. I have no idea. And it has nothing to do with nuclear fusion. And in fact, radiation pressure becoming a majority partner with gas pressure in very massive stars is what gravity loses grip on the star. Because why? Because photons have no mass. They have momentum. They have no mass. So if most of the particles that are exerting the pressure in the star are photons and not gas particles that have mass, the star will fall apart, or certainly be more easily disturbed into falling apart. In fact, this helps. This ratio here at high mass is what is a helping agent for setting the maximum mass of stars. As I said, I have no clue as to where this radiation pressure. This is actually the most recent misconception. This radiation pressure thing, and then oftentimes brought in and associated with nuclear fusion. As I said, he assumed that the simplest form of energy transfer, heat transfer through the star is radiative diffusion, whereby rate of energy slowly leaks out of the star. Very gradual process, like someone with a bottle of perfume over in the corner of the room, spritzing it, and then sometime later, someone over there notices someone put on perfume, because those little droplets of perfume are scattering around, taking random steps, scattering off the molecules of air in the room, and just slowly diffusing through the room. That's a complicated equation. So I wasn't going to go into get into that, but it turns out we can actually simplify that process into the simple relationship between a star's luminosity and a measure of the star's total radiation content and energy. You add up all the energy in terms of radiation inside a star. That's what E radiative is. If we divide it by the diffusion time, how long it takes for the energy by photons to diffuse through the star, from the center of the star out to the surface. Of course, once that energy reaches the surface, it just streams out into the cosmos. That's what we call the star's luminosity, right? And if you work it out, it turns out that you can relate the star's luminosity in terms of our sun's luminosity. It's a factor of about 40 out in front. It depends on this parameter here governing the composition of stars. So again, a hydrogen-dominated star has the smallest mu, and something made out of helium would have a higher mu, and something made out of carbon have, and so on, a larger one. It depends on composition. And then we factor of this 1 plus R here, which is where R again is the ratio of radiation to gas pressure. These both depend on fourth power. We have a cube relationship with the mass, so it's very sensitive to mass. Right? 10 times more mass, all else being equal, you get 1,000 times more luminosity. And there's this one more parameter here, down below, and that's the opacity. This is the radiative opacity, measured in those units. This value here is a weighted average within the star. And what's the radiative opacity? It's just the gas's ability to interact with light, to absorb light or to scatter light, and therefore to slow down its transfer process through the star. It makes the process of diffusion longer if you have larger opacity. This is like in conduction, or why you put on blankets to stay warm on a cold night. The more blankets you pile on, the warmer you stay. It takes longer for your body's energy to conduct its way, diffuse its way through the blankets. The blanket layer is thicker. So large kappa means a lot of thermal, in this case radiative, I'm trying to say, so a large opposition to the flow of energy by radiation. This value of radiative opacity is smaller for gases of higher temperatures and lower densities, and those are the conditions found in stars of greater mass. So the higher the star's mass is, on average, its temperatures are higher, its densities are lower. That results in lower radiative opacities. So their ability to transmit energy by radiation is more efficient, all else being equal. So more massive stars are more efficiently leak out their greater amounts of luminous energy. Why do they have greater amounts of luminous energy? They have more mass, more particles. The temperatures are higher. So the thermal reservoirs are bigger. More massive stars are more luminous. This is Eddington's relationship here in blue, plotting the luminosity of the sun here. I'm sorry, luminosity of the star in comparison to our sun versus the mass of the star, units of our sun's mass. So 1 here. So this is 1 unit of luminosity. This is 10, 100, 1,000, 10,000, okay, a million. And the relationship is this blue curve here. And sort of in the middle of this diagram, it scales roughly as mass cubed. But as you go to lower densities, the higher gas densities and lower temperatures, and those lower mass stars means greater radiative opacities are found in these stars, and so they have an increased opposition to the rate of flow. So the luminosity falls off more quickly with decreasing mass. And at the upper end, the greater importance of that term downstairs, radiation gas to gas pressure, to the force balance of the star, means that the temperature doesn't rise as fast with mass, and so the energy in the radiation field doesn't rise as fast with the mass, and so it rises less slowly, less rapidly than m cubed as we go to higher masses. Now this all works really great. If I were to plot a whole bunch of main sequence stars in this diagram, real ones, they pepper the diagram right along the blue curve. All right? This was 100 years ago. It does not accurately address certain classes of stars that transport their energy by convection, or possibly conduction in some cases. It doesn't address also these super dense white dwarf stars, which have a very different equation of state than something approximated as an ideal gas. They have so there's a different set of rules for them. But for stars whose main transport energy mechanism is radiation, this is a fantastic model, and it has nothing to do with nuclear fusion. We haven't talked about the physics of nuclear fusion in terms of the star's luminosity, and yet we can predict it. He predicted it 100 years ago. He had no idea how it worked, yet he invoked it to produce a state of energy balance so that the stars did not have to contract, so our sun could be around for 4.5 billion years at roughly its current size and luminosity. I just want to make this point here. It turns out that the power produced by fusion is almost always set by the star's luminosity. It's exactly the opposite of the meme put forward by the virus, misconception virus, which has the cart in front of the horse. It says that the star's luminosity comes from fusion and is controlled by fusion. If the energy coming out from fusion goes up, the star's luminosity goes up. That's what you read about. That's exactly the opposite of what's going on. So what is the star's luminosity all about? Well, it's thermal in origin. Our stars emit light because they come from hot, dense gases under the force of gravity that, because they're hot, they emit light. So it depends on the star's temperature structure. How does temperature change with radius for the star? Depends on modes of energy transport. Is it radiation, convection, conduction? Many stars like our sun, radiation dominates. There are very low mass stars where convection dominates. Stars in old age, convection again dominates. So there's different time periods and different kinds of stars where there's different modes of transport. So they factor in. And then, of course, the factors that oppose the energy flow. So radiation opacities or conductive opacities, how insulating your material is against radiation or conduction. The particle equation of state. How does pressure, temperature, and density vary amongst the particles that provide the pressure to support the star against the force of gravity? So, so Eddington guessed an ideal gas. That's the simplest possible model. That's actually not correct. Of course, by its very name, ideal gas, no such things exist. Okay, but there are many examples in nature where that's a very good approximation. In today's models, we don't assume an ideal gas equation of state. The convection dominates energy transport. Then we have to factor in the star's surface area and surface rate of opacity, in addition to its thermal energy content to direct its luminosity. In simpler terms, more massive stars have more particles and are hotter, and so are more luminous. And even in stepping back even simpler, why are stars luminous? Because they're hot. And the answer is, why are they hot? Because they are supported by pressure whose particles' kinetic energies depend on temperature. That's why they're hot. They're as hot as they need to be in force balance. So nuclear fusion is not in control of the star. If it were, that's what we call a bomb, as far as I can tell. This isn't a star. That's a bomb. In fact, that's a 20 megaton thermonuclear explosion of a hydrogen bomb from 1954 or something like that. Castle Bravo. Let me illustrate how energetically unimportant fusion is most of the time in a star. You sitting in your chair right now, through chemical energy of metabolism, moving electrons around in chemistry, are generating 2,500 times more energy per kilogram of you than our sun is on average from nuclear fusion. So are stars hot because of fusion? No. Here's another one. This one has to do with energy balance. Each second, hydrogen fusion generates the equivalent of 1 part in 10 to the 15 of our sun's thermal energy content. How do we figure that? Well, we compare L fusion, which for our sun is a main sequence star that's an energy balance, so these two are equal to each other. Power coming out from fusion is actually set and determined by the power radiated by the sun, its luminosity. That's the way to think about it. That value is about 4 times 10 to the 26 joules per second. Here's our sun's thermal reservoir right here. Hot gas, 3 times 10 to the 41 joules. There's a factor of 10 to the 15 between these two. Our sun only loses 1 part in 10 to the 15 of its thermal energy content every second. You say, what? Gosh, those are huge numbers. I can't manage it. What's going on here? So let's bring it back down to Earth, literally. Just 34 miles away, Lake Michigan. Has about 4 quadrillion liters of water. So about 4. So there's this same factor of 10 to the 15. if we have 4 liters of water leaving Lake Michigan, which in our analogy is the solar luminosity, and then entering Lake Michigan every second, and that's our analogy through nuclear fusion, energy coming out from nuclear fusion. And Lake Michigan, of course, is our sun's vast thermal reservoir. That's what's going on. We have all nuclear fusion needs to do is replace 1 part in 10 to the 15 of our sun's thermal reservoir every second, which is equivalent to this. 4 liters of water going to Lake Michigan, 4 liters of water leak out. Well, of course, it's the leaking out that's happening naturally. It's the 4 liters going in that nuclear fusion is providing. And then Lake Michigan's remains constant level. So nuclear fusion doesn't make or keep stars hot. In fact, energy supplied by the star by nuclear fusion generally keeps the stars relatively cool. Because when the star, if you turn off nuclear fusion, as we've already discussed a bit, then it falls out of energy balance. Now it's losing energy in the form of light. There's no source of energy inside, and so that star will undergo slow gravitational contraction. The temperature will go up because potential energy is going down, so kinetic energy is going up, and kinetic energy is temperature, and the star heats up. So fusion keeps the star cooler. Not only does it make it hot, doesn't keep it hot, it keeps it cooler than it otherwise would be as a function of time. Right? Because otherwise, the Kelvin-Helmholtz contraction mechanism would be taking place. By the way, your metabolism sitting there in your seat corresponds to a 5 solar mass star. Okay, per unit mass, they generate much more energy. We saw that the luminosity scales have a big power and mass. So a 5 solar mass star produces as much, about 1 watt per kilogram on average, as you do sitting in your chair. A fat joke? No. I'm just saying that you're at rest, and so you're not exercising, so your metabolism is kind of low. And so as Eddington realized 100 years ago, the energy from nuclear fusion merely replaces an extremely slow energy leak, which somehow most of us have forgotten. And stars are not bombs, no one calls them bombs most of the time. I've seen some articles where they've been described as nuclear bombs going off, and that's in the center of the star. But most of the time that's not actually used. But the implications of what are the misconceptions are that the stars are bombs. Stars are hot because this gas is hot because of the energy coming directly out of fusion reactions. So with nuclear fusion being at the center of all the misconceptions, some number of years ago, I thought, well, golly, we have all kinds of computational models that compute the structure and evolution of stars. Is there some way we can actually just turn the damn stuff off? Just turn off nuclear fusion and see how does the star behave? So one time about 5 years ago, I ran to one of our master's students, and turned out that she had a summer REU program at Michigan State, and they learned how to use this code here, MESA. Okay, this is a well-known and well-published stellar evolution and structure code. It's modules for experiments in stellar astrophysics called MESA. This is the Astrophysical Journal article here, the opening one for the code in 2012. And she said, I said, well, okay, what do you know about it? She said, well, you know what? I'll go and check. And she got back to me and said, hey, I think I can turn it off. So she did. And we've been looking at this since then. Then the pandemic hit, and all heck broke out, and things stopped, and we had to get back into it. We considered 1 in 20 solar mass stars. So that's like our sun's mass, right? And a massive star. And we considered sort of a standard composition by mass of 70% hydrogen, 28% helium, and 2% heavy elements. This is the beginning abundances of the elements, which is pretty standard amongst the gas clouds in the Milky Way galaxy and nearby stars and so on. We don't have any stellar rotation. Just to simplify things, we included some standard stellar winds and mass loss mechanisms and standard convection models when stars had convection. And so stars without nuclear fusion, what that means is, so all processes involving the weak nuclear interaction and the strong nuclear interactions that can change the atomic nuclei are turned off. There's no energy generated, no changes in composition. How are we doing, time-wise? Okay, well, we'll have to, if that's the case, then I should probably jump towards the end then. Okay. Let's see. I've got a bunch of stuff here, some background. Sorry. So we'll jump here. Here's a plot of a star's central temperature versus its density. And these units here, so 1 gram per cubic centimeter again is density of water, liquid water. And so this is 10 to the minus 2, so there's 1 gram per cubic centimeter, 10, 100, so on and so forth. These are the kinds of density we find in the interiors of stars, normally. Well, normally here, but later off over here. And if we turn off fusion, here's our 1 solar mass star, here's a 20 solar mass star. This line here, with a slope of 1/3, in this logarithmic scale diagram, temperature versus density, is the same slope as Eddington predicted 100 years ago. And so here are detailed calculations here of stars without fusion, evolving this from the lower left towards the upper right. Okay, in the case of the 1 solar mass star, it reaches a maximum temperature and falls over. In the case of the 20 solar mass star, it just keeps on going. So what happens this star here is that it encounters relatively low temperatures at pretty high densities. This is 1,000 times the density of water here. At this point here, the star's evolution crosses that line, and suddenly the electrons, the free electrons that are in the gas, floating around the gas towards the center of the star, begin to have kinetic energies that depend on density rather than temperature. And as such, in that state, those electrons act as huge thermal sucks, okay, on the thermal reservoir in the star, like they're all had straws sucking water out of Lake Michigan, okay, reducing the thermal reservoir in the star. So the electrons in this relatively low temperature for stars and high density states are parasitic on the thermal energy content, and so the temperature begins to bend over. It's not rho to the 1/3 anymore, but it reaches a maximum temperature and then falls over. So effectively, these stars just stop evolving. The contraction process just slows down to grinds to almost halt. All the temperatures, not just in the center, but throughout the star, are just heading for absolute zero. Oh, it takes hundreds of billions of years to get there. The more massive star, on the other hand, is above a critical mass, above which that same contraction process, which increases the density, of course, increases the temperature along the same slope of 1/3. But they reach such high temperatures that they cross this critical line here for this weird electron degenerate state at such high values in density that the electrons become relativistic, which means they have speeds that are heading towards the speed of light under those high density conditions. In that state, they don't suck the thermal energy out of the gas. And so the star is just fated to increasing density and temperature until something breaks. This is like, putting a weight on a metal structure, and you keep adding more weight to it. Something's going to break. There's a critical mass of about 4 4.3 times the mass of the sun that divides these two types of behaviors for the compositions of hydrogen and helium that we explored. And if you change the composition a little bit, that critical mass changes a little bit. When you get above that mass, the stars evolve like this, heading for oblivion. If you get below that mass, all stars do this. They cool off and stabilize. Let's just look at the figure. If you want to look over here, that's fine, but let's just look at the figure. So now what we've done is they've now added in red and in goldenrod here the same evolution of the twins of the two other stars with no fusion. Now these stars have fusion. They're doing everything as they're supposed to do with nuclear fusion going on in the red and in the goldenrod. And look, early on in the star's evolution, when densities are low, temperatures are low, they're identical. Surprise, surprise, because real stars undergo protostar evolution before they reach the main sequence where there's no fusion going on. So it's the same thing as our no fusion stars. And this, for our one solar mass star, there's a break taken. The star gets off the highway, takes a rest break. It's called the main sequence. It's about 90%, 80% of its life, fusing hydrogen into helium. And then over here, it takes another break, fusing helium into carbon and oxygen. It's a much shorter break. The break's maybe, it's only 50 million years instead of 10 billion years. Look at the overall trend. The thing reaches a maximum temperature, rolls over and falls and stabilizes. How about the high mass star? That's in red. That's the one with fusion. So here's hydrogen fusion. Again, this is the major stage of fusion in the star's life is hydrogen fusion on the main sequence. 89% of the star's lifetime is spent there. Here's core helium burning. When the new helium core gets hot enough from gravitational contraction in the core to turn on helium fusion at 100 million kelvins, right? 100 million kelvins. There's carbon fusion, neon, oxygen, silicon, and there's nothing stopping it. It's heading off in the same direction of oblivion as our non-fusion star. Now, I actually don't know we know what happens to 20 solar mass stars up there in the corner. They blow up. We call supernovae, core collapse supernovae. The iron core, the structural integrity of the iron core, its ability to provide pressure to support the star against the force of gravity gives way. And that's why the core collapses. Not because iron doesn't produce any energy from fusion, which is a very common misconception. That's an energy balance problem, not a force balance problem. A couple of points, or one point I want to make here is that the end states for each of these stars, this pair of stars, those pairs, they're essentially identical. The overall trends in evolution are virtually identical. I mean, not precisely, of course, because fusion does something to the star. It adds energy to it, which alters the structure of the star's evolution over time. But the overall big picture evolution of the stars are about the same. We're going to see this on the HR diagram just a moment. No. Start here. So, in the early 20th century, two astronomers, Hertzsprung and Russell, independently, American and Danish, independently discovered the Rosetta Stone of stars. Since then been called the Hertzsprung-Russell diagram, the HR diagram. This is it here. He's put the star's luminosity on the vertical axis and the star's surface temperature along the horizontal axis, although we plot it backwards for historical reasons. Temperature increases to the left. If we know luminosity and surface temperature, we also know radius. They're related to each other, the size of the star. Right? And these are really big stars, and these are really small stars. In fact, this line, every point along this line here is 100 times the size of our sun. Every point along this line is 1 times the size of our sun. It's equal to the size of our sun. And every star, anything along this line is 1% the size of our sun. This gray line is the hydrogen main sequence. This is the locus where every star of a given mass ends up fusing hydrogen into helium in energy balance. Here are two stars. These are the two no fusion stars. They begin their lives over here in force balance, there and there. They both decrease initially as they contract, decrease in luminosity as they contract, because their primary mode of energy transport is convection at that point. And as we decrease the size of the surface area of the star, its luminosity goes down when the star is fully convective. At some point, the star contracts to the point where convection is no longer efficient, and all we got left is radiation transport. And so at that point, then the stars evolve either upward or horizontally in this diagram of luminosity as they contract. So again, the contraction is in the direction of the arrows. And you can see that because these are big stars, these are small stars. You see the arrows are pointing, generally speaking, from this direction to this direction. And why does it happen? It's because as the star contracts, the temperature goes up, and that reduces the opacity, which is the ability of the matter to interact with light through absorption and scattering. And so the rate of energy flows through more effectively. The luminosity goes up. And if the opacity remains constant, the luminosity stays constant. So look at our one solar mass no fusion star. It crosses over here where it could have been it crosses the main sequence here, 34 million years of contraction. Doesn't stop. It's got no energy source. So you continue contracting, getting hotter, denser, reaches a maximum luminosity here at 60 million years, and the luminosity goes down. And why is that? It's because at this point here, the density on the inside of the star is high enough that the electrons down there are close enough together that they're generating a pressure, a gas pressure, whose kinetic energy of particles depends on density, not temperature. And so subsequent contractions of making the gas denser pulls the temperature down. Remember, these electrons act as huge thermal energy sucks. Okay, and so the insides of the star cool off, the whole star begins to cool off, and of course stars are thermal sources of luminosity, so the luminosity goes down, and they just simply radiate their thermal energy content away. It's almost like it's somewhat analogous to taking a white hot coal out of a fire and setting it aside over here in a cooler environment and watch it radiate energy away and cool down. And it takes hundreds of billions of years to do that. And the massive star, well, contracts, initially under convection, and then radiation, crosses the main sequence where if it was able to generate energy from fusion, it would stop for a long period of time. But instead, it just continues the contraction, heading off into oblivion. I want to make this point over here before going on to the last couple of slides. If Dr. Evil turned off nuclear fusion in our sun right now, our sun, which sits right in here someplace, would begin evolving along, roughly speaking, this dashed blue line. It would become initially more luminous as it became hotter, not just on the outside, but on the inside. You turn off fusion, and our sun gets more luminous. How do you explain that fusion controls and sets the star's luminosity? If you turn off fusion, the star becomes more luminous. You can't. There's no reason to. It's not a logical argument. It's a physical one. I'm going to skip through most of this. I'm just going to hit the highlights here. Now we've added in the stars with fusion. That's the goldenrod and the red again. They all start off in the same place. There they are. There's a protostar here. There's a protostar there, 20 solar masses. You see that the red and green are on top of each other through the protostar contraction phase. Why? Because the real star that eventually undergoes fusion doesn't have any fusion going on in the first part of its life. Mother Nature already provides this experiment for us. We've just somehow lost sight of this. As our sun and this 20 solar mass approach the main sequence, what that means is that hydrogen, the star is getting hot enough and dense enough in their interiors to begin cranking out energy from hydrogen fusion fast enough to begin matching almost, some fraction of the star's luminosity. It's beginning to catch up to the star's luminosity and to fill that energy loss hole. And just as it does that, guess what the star's luminosity does? It goes down. You turn on nuclear fusion, and the star's luminosity in response goes down. That's because turning on this source of energy down in the center of the star has to deal with this centralized energy generation source down there. It has to change its structure. And by changing its structure, that change in structure changes the star's luminosity and the direction downward. Our sun reaches the main sequence, 50 million years of contraction takes it to the main sequence. The 20-month solar mass star, of course, the more massive stars do everything quicker. They take only 60,000 years to contract to the main sequence. Once they reach the main sequence, they evolve. This is main sequence evolution here. So the star fusing hydrogen and helium in the central core is actually increasing in luminosity and becoming larger. Same thing with our sun. It starts off here, it goes up. This length here is the sun's main sequence evolution here. Both stars get larger in size and become more luminous. Why? Because hydrogen is being turned into helium. We're getting fewer and fewer particles in the core, and it's the particles that provide the pressure. So what's the star to do? To provide enough pressure down there to support the rest of the star. It pushes the star to not deciding on, by some thought process. The star figures it out. The envelope of the star, the rest of the star, moves away from the core. And so it doesn't bear down as much weight on the core, which is good because there are fewer particles down there while we're converting hydrogen into helium. That's part of it. Another part is by having fewer particles down there, there's the opacity down in the core of the star goes down. That also increases the luminosity. So both stars grow a bit in size. For our sun, the sun will grow probably 50% in size over its main sequence lifetime and increase its luminosity by a factor of 2-ish. And roughly speaking, it's similar for the more massive stars, a bit more changes. And our sun will do this for a total of 9.5 billion years, so about halfway through. The 20th solar mass star will only last as the main sequence star for something like 7.5 billion years. 7.5 million years, sorry. Factor of 1,000 smaller. And the reason for that, again, is because the two stars have very different luminosities. If stars are in energy balance, L fusion equals L star. 20 solar mass star is 10,000 times more luminous than our sun is. So the 20 solar mass star has to crank out energy from fusion that much faster. Now the main difference between stars with fusion and stars without fusion, you see the green star goes off that way, and the star with fusion goes off this way. Our star without fusion keeps going around this way, whereas the star with fusion goes off that way. But both stars move in the direction of becoming very large, giants and supergiants, in old age, fusing helium into carbon, and so on into other elements. Our sun only gets as far as helium burning into carbon, whereas this star will go all the way up to iron. Both stars become extra large in size. Why? Because their cores now are the big blobs of helium sitting down the center there that weren't there at the beginning. And for the star to remain in force balance with this big, massive helium core, the envelope has to get distended. And there are other reasons too, but we need to get into those. Just continuing along. Eventually, our sun will stop fusing helium into carbon and oxygen. It won't be able to do anything more because why? Because you saw before, the carbon and oxygen core hit a maximum temperature and roll down. It never reaches the temperature to fuse carbon, so our sun will stabilize as a half solar mass carbon-oxygen white dwarf. There's some mass loss that takes place up in these very, very large parts. So this is a large star. These distended outer envelopes lose mass because the surface gravities are very low. Same thing for the massive star. Up here, the star loses half of its mass. Our sun stabilizes as a half solar mass carbon and oxygen white dwarf, evolving this diagram much like the no fusion star for 1 solar mass. The high mass star, they do go off in opposite directions here, but their fates are the same. It's catastrophe. Because in both cases, their temperatures and densities keep going. You're just adding more and more weight to this metal bar hanging off over here. And the thing is straining and straining, and it's not straining as much or stressing as much as it was. Eventually, it's going to break. That's how the equation of state works, whether you're talking about a solid metal bar or a structure of a bridge or the structure of a star against the force of gravity. Now, we're going to finish up here because I want to make the big point. I've made a lot of points about how we minimize, or how we should have a different perspective about the role of fusion in stars. We've put it out in front. It explains everything about, you ask any question about a star, it's nuclear fusion. All right, and we tried to address that. There are some very important things that nuclear fusion does do in a star. So this is the luminosity of the star versus time, or the stellar age of the star, rather. And this is the 1 solar mass star, the 2 twins, the no fusion object, and of course the goldenrod is the fusion one. And then the green one is the no fusion for the 20 solar mass, and the red one is the 20 solar mass for the fusion star. You can see again, the early evolution during the protostar stage is exactly the same for both fusion and non-fusion. You can see the drop in luminosity just before the star reaches the main sequence. You can see the drop in luminosity just as the star reaches the main sequence. The no fusion star increases in luminosity, reaching a maximum value, and just cools off and fades away over 100 billion years of time. The 20 solar mass star, we're also including what's called the total luminosity, which also includes neutrinos. Once in these massive stars, they reach temperatures that are not only hundreds of millions of degrees, but billions of degrees. At those temperatures, the plasma is not only emitting photons, it's emitting these little subatomic particles called neutrinos. As the name implies, they're tiny little neutral particles that weakly interact with anything. And once emitted in the star, those neutrinos just stream away from the star. Even if it's emitted in the center of the star, it just goes right through the star, because very few neutrinos will actually interact with normal matter of charged particles. And late in the star's life, whether it's this star or that star, no fusion or fusion, once they reach temperatures of 500 million degrees, they become neutrino sources. They actually have higher luminosities in neutrinos than they have in light. These are neutrino stars, not in terms of their total luminosities, they are neutrino stars. In any case, the emission of neutrinos just speeds everything up in the star's evolution late in life. And these guys, okay, again, they go off into oblivion, and their equation of state breaks. The metal bar with all the weight hanging off it breaks, and the core, the center of the star collapses. I actually don't know what happens to a non-fusion star, because remember, these non-fusion stars are made out of hydrogen and helium. That star is about the size of 7 times the size of the Earth at the point of collapse. It start off being, 5 times the size of the sun on the main sequence, as a main sequence star. Okay, but it ends up as a fraction of the sun, a few times the size of the Earth. It's a super dense object. I have no idea what happens to such stars made out of hydrogen and helium, but they undergo collapse, that I know. So it comes to some kind of catastrophe. These stars actually blow up as part of their gravitational collapse of their iron core. And you can see there's a factor of 33 gain in luminous lifespan. These stars last only 250,000 years. These stars last about 8 million years. So there's, a big straw in the hat for fusion. Stars are much longer lived as luminous objects. Likewise for the 1 solar mass star. This will never actually, either one of these things meets a catastrophe. They simply fade away. as the degenerate electrons begin to suck out the thermal energy content in the star, they just cool off and just fade away. They're just heading for absolute zero over hundreds of billions of years. But if we so here's the main sequence lifespan here, 9.5 billion years. And if we sort of count, I don't know, I'm not sure where you want to stop the luminous lifetime of the non-fusion star is, but here's one solar luminosity here. Here's a tenth. Somewhere in there, it's probably say, well, the star's going to fade away and its lifetime's over. Let's just count it, not luminous anymore. And so roughly about a factor of 100 gain here in luminous lifespan between the fusion star and the non-fusion star. All right, so this is the last slide. The first takeaway is that Mother Nature already provides this experiment. We just need to look at the contraction of a protostar before it's hot enough to convert hydrogen into helium through nuclear fusion to see how stars evolve and where the luminosities come from and so on. These stars are in pressure-gravity balance, despite the fact that no energy coming out from fusion. There's no pressure, there's no magic pressure coming out from fusion, because there is no fusion. And then, of course, there is no magic pressure coming from fusion, radiation pressure or not. But they're not in energy balance, and so that's why they contract. This is a very, very gradual process by comparison to a collapse due to a lack of force balance. Gravitational contraction is not the origin of, or neither is it control, the star's luminosity. Again, this puts the cart in front of the horse. You'll see time and time again that the protostars are luminous because they're contracting. That's not why they're luminous. They're luminous because they're hot. And why are they hot? Because they're supported by pressure whose particles' kinetic energy depend on temperature. That's why they're hot. And they're in force balance. Instead, the luminosity controls the rate of contraction. It's just the other way around. The rate which a star contracts is controlled by the rate it's losing energy, which is the reason why it is contracting, because it's losing energy. As we mentioned, the star's luminosity actually drops by about 30 or 4% in the last stages of protostar evolution, just as it's approaching the main sequence. As it's just now cranking up some energy from hydrogen fusion, the star's luminosity goes down. Once the star arrives in the main sequence in energy balance, meaning this, the same expression that Eddington wrote down 100 years ago, although he didn't know how it worked. The star's luminosity controls the rate of energy that nuclear fusion generates, which is, as we see, is a mere trickle compared to the star's vast thermal reservoir. Remember that 4 liters going in, 4 liters going out, Lake Michigan? That's what fusion is doing for a star. Well, for our sun, a more massive star that's much more luminous, the rates going in and out are bigger. So what are the rules of nuclear fusion in stars? What are the ones we should be talking about instead? Exothermic nuclear reactions dump energy into the star that allows it to achieve energy balance, slowing down the star's gravity-driven evolution by a factor of 100. They last a lot longer as luminous sources of light in the cosmos because of the energy going in from nuclear fusion. That luminosity is not controlled by fusion. It's just dumping energy into the star, which all that does is it delays the action of gravitational contraction to sending the star to its final fate, whether it's a 20 solar massive star to a fate of catastrophe, or the low mass stars to the fate of absolute zero. The consequent drop in the number of particles in the star's core where fusion is taking place results in the star's evolution in structure, and that happens to maintain force balance. And those changes then result in a change in the star's luminosity, not the other way around. Of course, we're all standing here, made out of carbon, a bunch of water, hydrogen, oxygen, right? Phosphorus is important to human life function, lots of other elements. Fusion and other nuclear reactions produce the rest of the periodic table beyond hydrogen and helium. That's obviously very key to the cosmos we live in. So it's gravitational contraction and the leptons. Leptons are the electrons and the neutrinos. These two particles here, they control this big picture, as far as I can tell, the big picture evolutionary fates of stars, whether they're fusion stars or non-fusion stars. This is basically the big picture of how stars evolve in time. They're controlled by gravitational contraction and the actions of electrons and neutrinos. And there's a critical mass below which a star will revolve in one way and head for the icebox as a white dwarf, above which the core of the star heads for oblivion and the equation of state breaks. This core collapses. We have a catastrophe of some kind. There we go. I want to thank my collaborator and also several students I've worked through over the years, including most recently a student here at Kalamazoo, who I'm still working with right now on this project. And thank you all for coming out tonight.